Okay, so the topic today is path tracing in two languages. One is obviously C++, otherwise why are we here? And the other one is OCaml. And I am an intern at SketchUp for about a year and plus 3 months. I'm also a computer science and applied math student in C border. This year will be my last year. I love computer graphics, especially for retracing stuff. So that's why I'm excited about talking more on retracing. Before I continue, I just want to mention, if you have any questions, just interrupt me and ask. Questions, comments, concerns. Now let's talk about OCaml a little bit. OCaml is static typed language, just like C++. It have a Hindley-Miller type system, which basically means the type can be inferred almost everywhere. If you are familiar with languages such as Rust, Haskell, etc., then you are familiar with this kind of type system. It is different from C++ auto, which can only infer forwardly of the types. OCaml is also garbage collected, just like most of the programming languages nowadays, but not C++. It can compile to both bytecode and native target. Bytecode is kind of easier to use, but obviously slower, and native is just like C++. It is strictly evaluated like most programming languages. And OCaml also have a very similar philosophy of C++ in that it is multi-paradigm, but it supports functional programming first. After that, it also supports object-oriented style, imperative style, modular style, etc., etc.
Leslie, I'm not familiar with the term strict evaluation. Could you clarify that for
It's
me?
also called eager evaluation. So it's basically when you have an expression, you just evaluate it right away. Okay. Instead of like waiting to the last minute and lazily evaluate it.
Okay, thank you.
OCaml and Haskell are commonly like compared to each other, and like sometimes people say OCaml is the eager Haskell.
Okay, and in Haskell everything's default lazy.
Yeah.
All right, thank you.
Yeah, I like think those two languages are very different. So not just about the strict versus lazy, but also a lot of other stuff. And it has one of the most impressive module systems I have ever seen. I put one off here to play safe because obviously I don't know much of programming languages, but for all the languages I have personally used, it has the most impressive module system from all the languages. Here is a quick history on how OCaml come to be. So the first untyped functional language is Lisp, from 1958, and that language directly influenced another language called ML. ML stands for meta language, not machine learning. And ML kind of is a really influential language that impact a bunch of other languages. So that's why we have a box, put it as an ML family. Yeah, standard ML that's still used somewhere in academia, and I pretty enjoy this language. Also CAML, which is categorical abstract machine language. This is a direct ancestor of OCaml. And OCaml just add object-oriented features into CAML. That's why it comes from. OCaml also directly influenced a bunch of other programming languages, such as F#, starting from a fork of OCaml. And OCaml, I put it as a smaller font here because it technically is not a programming language because it shares the same ASD with OCaml, just the syntax is different. and Rust are heavily influenced by OCaml. There are some other stuff here, like Miranda is a lazy functional programming language that looks a lot like Haskell, because Haskell is directly influenced by it. It also influenced by ML families. There's Scala and Elm. All of them are benefited from the ML family. So all of those kind of like looks like happen in a parallel universe except Rust, but for us. But actually, if you look at the D&D book, Boyani mentioned that when he designed template, the thing he consulted is ML generic and Ada generic. So it also influenced C++, just not as big as some of those languages. So OCaml is initially designed for symbolic computations like Darren provers, compilers, interpreters, static analysis, etc. This is the initial use, and OCaml are really good at this stuff. But people also find OCaml useful for all kinds of applications like data processing, finance and trading, business applications, web. There is a transpiler called BuckleScript that transpile OCaml into JavaScript. And also even system programming. So how does OCaml look like? Here is a very simple function, map function on a list. It basically apply a single function f into every element of that list. In OCaml, when we need a recursive function, we need this explicit rec keyword. A lot of people may find this annoying, but it is actually a feature of OCaml and combines pretty well with some other features of OCaml. Then we have pattern matching of, if the list is empty, we just return empty list. If the list has a head and some other tail list, then we first run this function on the head element of the list and then recursively call the map on the tail. Notice this function keyword is just a syntactic sugar of pattern matching on the last element. In this case, I don't even name the last element. Instead, I just use this function keyword. In OCaml, when we need to introduce a new variable, we need to use let binding. This is a lot like, for example, F# or other ML dialects. We have seen with the let r equal to something, like just like when we initialize a variable in C++, in and followed by another expression, because OCaml is expression oriented. So we cannot just put this in is like semicolon, but we must follow another expression after the in. We cannot just have semicolon and down here. Now, that function works on the OCaml's built-in linked list. What about if we have our own list? Then we can define a list through a variant. So if you ever code a linked list before, it should sound familiar. A linked list is either nothing, which in C++'s counterpart is no pointer, or a node that contains one element plus the rest of the list. This column A is the generic syntax of OCaml. So in OCaml, when we have generic syntax, we put the type parameter before the generic type. So in C++, we will have my list angle bracket, and A is inside. But in OCaml, A is put before the actual generic type. And then our node is a tuple. where in OCaml start means the tuple type. And in this case, the tuple is one element and another list. Now map function looks like following. It's almost exactly the same as the previous map function. We just changed the empty list and the console into our customized list. So we can see pattern matching is really good at variant because the code is basically as nice as built in. But now we have a problem. We have two different map functions in the same scope. In C++, we will expect this to be an overload set. We just have two map functions, and what will be called will depend on the type. But OCaml does not support any kind of function overloading. Instead, what will happen here is the second map function will hide the first map function. So this is name shadowing, and clearly undesirable in this case. To solve this problem, the next thing of OCaml is modules. And we can introduce two different modules to the OCaml that the first module wraps the built-in list, and the second module wraps our custom list plus a function. So module in OCaml have a lot more functionalities than the C++ counterpart. It's used as both like C++20 modules. Also, it's used as namespace to just organize code. And it also, a lot of time, it can be used as a class. And we will see more about this stuff later. Sorry, are there any questions or just random noise? Okay, I will continue. In OCaml, it is a naming convention to put a type related to module as T. So usually we just have one type associated with a module. In C++, a class itself is a type, but in OCaml, we need to explicitly put a type that belongs to that module. Now, the next question for C++ folks naturally is, we have two modules. They looks almost the same. Can we use them into some generic functions? And the answer is we can. First, we need to create a module type, module interface that's called mappables, because our two lists, the commonality of our two modules, like they both have this map function. The syntax is a bit weird with the sig and end. That is because OCaml is a white space insensitive language, so it must have some keyword to distinguish where a start of block at and where the end of a block is. But it also doesn't have curly braces, so sometimes it has weird syntax. This module interface is like concept, except it is required, unlike concept, because concept constrain on the template parameters, but this module interface enable what basically a higher ordered module can do. Then we can have an OCaml feature called functor that allows to dispatch on whatever module we pass in statically. Functor is a really unfortunate name because OCaml functor has nothing to do with both C++ functor. I'd rather not C++ folks not call it functor, but also Haskell function. It is completely different. And the way to think of it is a higher ordered module that takes a module and we add additional generic functionality to it. In this case, we add an increment function. I should call it increment, not class, and just add 1 to all the elements inside this list. And then we can explicitly instantiate this incrementer into ink list and also like incremental of my list. Then we can just use it normally. So far the OCaml module like a lot of like C++ template. It is totally a compile time thing. This function stuff is totally compile time dispatch, and there are no interaction between the value language, the normal value and type language with this module language. This module language is like totally stratified. The module language understands the type and value, but the value language doesn't understand modules. Similarly, like in C++, the normal C++ don't understand template. The template understands normal C++. We will see this can be changed later when we introduce first-class modules in OCaml. But first, let's talk a little bit about retracing. Retracing is not a single algorithm. It is instead a set of algorithms that share the common tracing the array idea. It starts from 1984. Tuna Whitted first introduced retracing into computer graphics, where he sent one ray per pixel, and when it hit an object, it will send a shadow ray towards the light source. Because it sends a shadow ray to a light source, the light source must be a point light. It cannot be anything fancier than that. And we will have hard shadow. This is the main artifact of the weighted retracing. The shadow is just solid. And then the next evolution is stochastic retracing, which just send a bunch of shadow rays toward the light source. Then we can see the light source is actually an area, and like all the light sources in the normal world. Then, because of that, we can have soft shadows finally. The next evolution is path tracing by Kudrea in the render equation paper, which not introduced path tracing, but also something more fundamental called the render equation that I will not talk about today. But the idea is we just ditch the idea of shadow ray altogether. Instead, for each pixel, we send a lot of rays. And then those rays will just bounce off until we hit the image. So the path tracing is the algorithm we will talk about today. The basic idea of path tracing is for each pixel, first we create a number of samples for that pixel. This is usually just created uniformly distributed on this pixel, on the pixel rectangle, but there are fancier strategy, like you can stratify the pixels into little sub-pixel block, and one sample can only be generated on that block. And then we shoot this ray, shoot a ray at this sample. When the ray intersects with any object, we reflect or refract the ray randomly depending on a distribution function. The distribution function is like the property of the material. For example, if we have a mirror, then you expect the light to have almost perfect mirror reflection almost all the time. On the other hand, if we have dirt, for example, then we will just expect the light to scatter almost randomly. We will recurse the last step until the ray hit a light source. And then we calculate the radiance accordingly. The radiance is just a fancy term of the intensity of the light. In this code, I just use RGB triples to represent the radiance. And RGB color is a good enough approximation for most graphic applications. At the end, we average the radiance of all samples to get the radiance of this pixel. Here is a visualization of what's going on. We shoot a ray. it hit an object, then this will just scatter, and it hit an object again, it scatter until it hit a light source. And then we calculate the color accordingly. And here is another visualization. What's going on with all the samples is we calculate a bunch of samples and we get different color on each sample. And then we average the colors of the samples to get the final color for that particular pixel. So the code I'm following is the retracing in Weekend book. The book written by Peter Shirley. He's one of the demigod of the retracing field. And I had two implementations. One is the C implementation when this book was just out in 2018. And another is the OCaml implementation that is currently in progress. I live coded it in YouTube stream like once a week, but I was being lazy for the past months. It does not implement everything in the original book or the C implementation yet. That is my final goal though. But what we will see is already implemented in this code. There are a bunch of utility classes or modules depending on languages. We have 3D vectors, rays, and cameras. Those are just basically some struct, and I will not show those code because it's too easy and boring. And the first interesting part I will show today are shapes. So we need some dynamic polymorphism to represent shapes. If we want different kind of shapes and later we need to put them in a tree structure. There are ways to avoid dynamic polymorphism if you are using OpenCL, you must, but there are no benefit to do that for a CPU reducer. And the property we want for this kind of dynamic polymorphism is easy to extend, that we can just add more and more shapes without touching any existing code. So variant is out of question because it works on a closed set of tags. Instead, in C++, we will just use inheritance. In this case, we have a base class called shape. And in OCaml, we will use something fancy called first class module that I talked before. So you're probably familiar with first class functions, this term, where C++ is lacked, but most programming languages have. Basically, we can treat functions as a value and pass it around. But first class module is something unique to OCaml where we can actually treat a module as a value and pass it around. This may sound really strange, like module is not a compile time thing that just used to organize files, but when I first saw it, it's totally blew my mind. But it actually is a really cool way to introduce dynamic polymorphism in OCaml. The essence of both of the code are the interface of the shape, that we have one intersection function, which we call shape, that pass array and some range of intersection. Then we say we return optional to say if we intersect, then we return a hit record. Otherwise, we just return nothing. Similarly, in the OCaml implementation, we pass those range and array. We pass additional t here because in OCaml there are no like class functions. This hit function must take a shape by itself. So in C++, this process is implicit by this pointer, but in OCaml we need to explicitly pass it around like this. And this type T is just the type associated with the shape. In this case, it's just any shape. And finally, it returns optional heap record. And we also have a bounding box function that, given a shape, we return the kind of rectangular bounding box, which we call ABB. It's axis aligned bounding box. We will see how bounding box can be useful when we talk about the bounding value hierarchies. But there are a lot of boilerplate in both versions because I think both languages want to punish you by using dynamic polymorphism somehow, by saying this stuff is not what you should do by default. In the C++ version, we need virtual destructor. I also deleted the copy operations to prevent slicing. And I delete the move instruction, move operations totally just to make client-ID happy. I don't see any possible reasons why deleting move can actually help, but it makes client-ID happy. And in the OCaml version, we have another module type called shape instance that bundles the module itself. And then we create a value of that module and then bundle both of them together. Then we need this explicit build shape function that we need to pass a polymorphic type parameter in, and then explicitly have type constraint of the shape type T, because this is one of the cases where the type inference of the OCaml cannot understand what is going on because we have dynamic polymorphism. So in this case, we need the explicit type constraint. And of course, we need to pass some shape in, but some non-polymorphic shape. And then we just create this first-class module on top of it. This function is kind of like, if we talk about a C++ equivalent, it's kind of like a template that takes different kind of classes and then box them into a single value and return. It's the same kind of stuff. I will talk about sphere because that's the easiest shape to implement. A sphere is a center and radius. It also has a material. So in C++, it is a bunch of struct field. In OCaml is similar. We define what we call a record. It is basically like a struct without the ability to put a function into it. A record contains center, radius, and material. We even have a similar constructor function, even though in OCaml it's just a free function. And then we have, in C++, we have this hit function that overrides with the base class hit function. In OCaml, we have this hit function that do not have any explicit override. But when we pass the sphere into the shape first class modules, then we need to satisfy this constraint. So this is checked automatically, just like, for example, stud function or any type erase the type. Now let's talk about the entry point of both programming. I skipped a bunch of boring stuff, but the idea in the C++ code is we just have a nested for loop to get an index for each pixel, and then for each pixel we have another for loop for each samples. I think in the OCaml version, it is similar for the nested for loop part, but OCaml does not support for loop at all. Instead, we need to use something similar to ranges, and sequence is lazy. So It is a lazy range, just like range views in C++ 20, where we have one range is the width, another range is the height. I don't like this code as much as the C++ code, to be honest, because it is hard to figure out whether this range is inclusive or exclusive, especially when it's decrementing. And also the Cartesian product is a bit confusing. Cartesian product, by the way, is not in C++ 20 ranges, but it is in range v3 if you want to use it. Then we, OCaml code, the final step is just iterating through the ranges, the 2D ranges we set up. And then the next step is for each samples, we create a random sample, which is a random point on that pixel, as I said before, and then we let the camera to generate a ray on that point. Finally, we just trace that ray using the ray color function and then accumulate the result.
I have a couple questions.
Yeah.
I noticed that you made your random number generator thread local.
Yeah.
In the C++ version. I'm just curious, did you end up using threading? Like the use case of making it thread local. Yeah.
Yeah, C++, this code is really simplified. C++ version, I actually use some tile-based strategy with threading on them, and this C++ code is really simplified.
Okay.
And yeah, one thing that worried me about this OCaml implementation is this random function is a lot like C standard library ren.
Okay.
It is global mutable, so it is as unfunctional as you can get, and it will probably cause trouble when I need to parallelize stuff. But unfortunately, I'm very spoiled by the random headers. Now I only see problems with random headers, and everything else in other languages are just crap.
So and I'm also curious, what is this let? I see the let u equals blah, blah, blah. And why and v equals this instead of two let statements or?
There are no differences in this case.
Okay.
This basically prevents me to use u in v if I use this let syntax, but it doesn't make any differences.
Oh, so, okay. It's like almost scoping or something right there momentarily.
Yeah. It's like introducing u and v in the same scope instead of have u first and then v.
That's interesting. Okay, thank you.
Now let's talk about tracing a single ray. First, we have some recursive limits. If I have depths too far away, then we just return black. Notice in the C++ version, I use a bit of stronger types with colors, but in the OCaml version, I just use vec3 for colors, for points, for vectors. But I will change this later. Then we have an intersection test with the thing of the current ray. If we hit something, then we scattered the ray depend on the property of the material that we returned from this hit function. And then we just call this function recursively and accumulate the color. If we don't hit anything, that means it is background. Well, it's not background, it just means we scatter into some other place, and then we just returns zero vector. The OCaml version is similar, but we use pattern matching instead. Notice the begin and end keyword here. Because OCaml don't have any way to distinguish if what's inside the pattern matching is the inner ones or the outer ones, we need the additional pair of keywords to distinguish that, to just like curly braces in C++. And if we don't intersect with any geometry, we just return the background color. In this case, the book returns a color that looks like a sky. And for materials, again, in C++, I use polymorphism. You use inheritance for dynamic polymorphism. In the OCaml version, I use variant for now, which may not be a good choice if I want to add a bunch of different materials, but it works for now. Later, I may probably refactor it into first-class modules. And material only have one function, which is scatter. Scatter the ray input ray based on the property of the material and the information heat record we get at that particular point. I will only talk about one kind of material because it's the dumbest. So I don't need to go into a bunch of math. Lambertian material basically scattered randomly about an array. And in C++ version, I changed this code a little bit. The original code don't use the designated initializer because it didn't exist at that time yet. But I changed it a little bit to use designated initializer. And in the OCaml version, it's kind of similar. We just have two let bindings and then return a record. So what we do in this code is we have a normal vector point outward, which is also a unit vector, and then we have another unit vector offset. After that, we should get a point on that unit sphere, and that will be the direction we want to scatter our ray in this Lambertian material. And we haven't talked about how the sphere is actually implemented with intersections. So here is a demonstration of what can happen. One is when we have a ray that does not intersect with the sphere at all. Another possibility is we have a ray that intersects with the sphere with only one intersection point. And also another possibility is we have ray intersect with the sphere with two intersection points. We don't need a special case for this one, actually. We can just use the code for this one to handle this one. But there are also another possibility not in this graph, which is if we have a ray shooting from inside the sphere. And in this case, we will get to root 2 points, but one of them is behind the ray, so we need to discard that. The way actually to calculate this kind of intersection point is quadratic equation. I will not show the details of how quadratic equation work, but basically I call this quadratic function and with a bunch of math to figure it out what different parameters is. If we don't have any root, then in this case is our first case in the previous diagram, we just return nothing. In OCaml, we use this monadic bind function. It is called and then to say, if we don't have anything, we just skip. Otherwise, we forward into and run this function, run the following function to achieve the same purpose.
Do you know what the status is on the nomadic interface proposals for standard optional?
No idea.
Nomadic. I keep saying nomadic. Monadic. Okay.
Yeah, it's a useful feature. I certainly hope it get in.
Yeah.
But also, I already have a customized optional implementation that implements all of them plus more. So, but I cannot use it in my job, just my personal project. And And then we first track the smaller root. If it is in range, then we use that. If it's out of range, that means we are probably shooting the ray inside the sphere, then we use a larger root. OCaml code is similar, but unfortunately, OCaml's option library don't have or else, so I wrote my own. And with that, I have this higher order function. No, not higher order function. It's just a nested lambda that with basically a root, and then I calculate the hit record from it. Notice if we have the first smaller root, then we are doing front face. Otherwise, we are doing the back face of the sphere, and we need to negate the normal. It's hilarious that those two codes. When I read this code, I didn't consult this code, but I have exactly the same kind of implementation 2 years later with this exactly same function name. And they are different from the book. The book just duplicates the code. Now, the last thing we talk about is bounding value hierarchy. So if we want to do array and a lot of object intersection, one naive way to do that is to just put every object inside a vector and loop through all the objects. But that is an OM problem, and it can quickly get too expensive. Instead, we can organize the object into a tree structure, like this. And if we have an array that does not intersect with the outer large box, we don't need to check what is inside. And similarly, if we have an array that only intersects with this box, we don't need to check this box. What is inside this box? And this is the basic idea. It's a lot of similar to the physics simulation where people do collision detection. But instead, in this code, we change the OM problem into log n. For collision detection, we change the problem y n squared into n log n. It's similar. The idea is to have a tree. The tree have left and right node, which need to be polymorphic. Didn't have any additional slide for, and also a bounding box, because we need bounding box to check whether we need to look into this node or not. In OCaml, we need some funky recursive module here, because our node needs to construct itself. And OCaml does not like that. To combat this problem, we need a recursive module. Inside recursive module, we can create another module with the same name. And because the module is recursive, OCaml's type system cannot infer what the signature of the modules is anymore. So instead, we need to add an explicit signature. In our case, we need our module is a shape, and we also explicitly put its constructor in. And for the bounding value hierarchy constructors, we first just get messed up with this slide. We first just randomly pick an axis. This is the implementation by the book. It is a really bad implementation for bounding value hierarchy, but it is simple. And again, in the C++ version, I use a thread local random number generator. And in the OCaml version, I use its random module. And both versions use some higher order functions, but in different granularity. In C++, we want to sort an object based on a certain axis. In C++, we just use lambda that calls the sort, and we pass the member pointer in to decide which axis it is. And in the OCaml version, instead, I create this compare shape by axis function. It is a customized compare function, which in the C++ is basically this part. So then we will just say compare depend on different axes. The rest of the code is just split the object to left and right. Case 1 and 2 are just special handling. For all the list with more than 2 objects, what we do is find the midpoint and split the object into two parts, and then just stuff them into the left tree and right tree. And finally, we need to calculate the bounding box. So we just merge the left bounding box and right bounding box. I really want to call this function union, but I can't in C++. In OCaml, I call it union. And the last thing is the rebounding box intersection. Again, first we just check if we intersect at all with the enclosing box, because if it is not, we don't need to check what is inside. Then we do the left part, do the intersection test of the left part and right part together. Notice in the OCaml version, we have this explicitly of unwrapping of the higher order modules, first class modules. This is a bit unfortunate, but this kind of syntax is only required when you use first class modules. And I also have some code for the short circuiting. Basically, idea is if I have intersection with the left box, then when we do right box intersection, I don't need to start from scratch, but instead I can just start from the intersection point. I have some benchmark, but it didn't show any improvements, at least in my benchmark. And finally, we just do some pattern matching that pick the closest intersection of the left and right. And for the C++ version, because we don't have pattern matching, we have this a bit nasty if, else, if structure. I can, of course, use ternary, but no.
Yeah, I think between the Rust that I've been playing with, the F#, and then your OCaml examples, I get sad every time I see these pattern matching things. I want this now.
Yeah. So that's everything I want to talk about. For the C++ implementation, since I like random, yeah, I know random have a lot of problems. Like the distribution is not deterministic. It's also don't have the best RNG we can, but it's still way better than most the random libraries other languages ship. Operator overloading, it is convenient in the OCaml version because it does not support any kind of this kind of overloading. Sometimes the notations get funky. Things I don't like, sort functional does not support magnetic operations. There is proposal in place, and also in my personal work, I just use a custom optional implementation instead of sort optional, and then I can use magnetic operations. Inheritance, that's more like I just don't like inheritance, but actually in this particular use case, inheritance does not means anything kind of bad practically. So I'm fine with it, just I'm not happy with inheritance is the most convenient way in C++ to do dynamic polymorphism.
Did you consider using a variant of all the possible shape types or something like that, like you?
Yeah, but as I said before, I want this to be easy to extend.
Right. Okay.
For the OCaml implementation, the things I like is pattern matching. The pipe operator that pipe one function to next. This pipe operator especially works well with things like ranges, which C++ provides a pipe operator, but it only works for ranges basically. And first-class modules are cool, even though the syntax is heavy. Since I don't like the no ad hoc polymorphism, for example, function overloading, all things in Haskell like type class, for example, OCaml has none of them. Instead, every time you need to statically dispatch on two types, and with different behaviors, you need two functions with different names, basically. OCaml's implementation is also slow, very slow. It's like maybe 10 times slower than the equivalent C++ implementation. I think the main reason is all the boxing being done in the OCaml. It box float, and also all the vectors are add additional boxing, and in C++ is just everything is layered on the stack. Also, the random number generator, I'm not happy with how it's used global multiple states. Okay, thank you.
Awesome, thank you, Leslie. Does anyone have questions?
So how easy would it have been to interface with, let's say, the C++ rather than the generator?
Sorry, what?
I'm just wondering how easy is it to interface with C++ code from OCaml? So, for example, could you have used a C++ random number generator?
I haven't played with that, but since OCaml is used for system programming, I assume it's pretty easy to do foreign function calls, but I never played with that.
And did you try you said it went on to, a byte language. That's the Java byte language?
No, it's its own.
Oh, okay.
I have a couple questions that are slightly tangential, although they were about things you mentioned in your talk, but they're not super C++ related. You mentioned that in your historical diagram of OCaml, that OCaml was what led to influence Rust, not Haskell. And I've heard both, mostly on different podcasts. But there's a quote that I tweeted out once that Rust is the love child of C++ and Haskell, which isn't consistent with this diagram. So my question is it like more or less widely agreed upon which language actually influenced, or did both, or is it one or the other?
It's both. But this diagram is very OCaml oriented.
I see. So it wouldn't be incorrect to say that Haskell also influenced.
Yeah.
And then a follow-up question. You said earlier that you consider Haskell and OCaml quite different. Do you want to elaborate? Because I'm only like a surface level, although some people refer to me as the Haskell guy because I bring it up in my talk so much. But really, like I'm a very like surface level. I have a surface level understanding of Haskell, like more than most. But I don't know anything about OCaml other than that I've heard that it's like the eager Haskell. So like, what do you consider like the big differences?
So I think for the philosophy-wise, Haskell is designed, they want the best lazy evaluated language possible. They want this language to be very kind of elegant. OCaml is a lot like C++. They want a language that works for people. And also another thing a lot like C++ is they just add different ways to do the same stuff. They have subtle different trade-offs. It's a lot of, the philosophy is very different for two languages. Also for feature-wide, I think the Haskell is obviously lazy, but the other big thing of Haskell is type class that change a lot of how things are being done. In OCaml, I think the most unique features is module. Just like all the languages in the ML family, except for F# because it's basically get rid of the ML module and instead use the kind of .NET modules. But all the ML languages have very complicated module system.
Cool, thanks. And this was, I really enjoyed the talk, so thanks for giving it. I love this introduction of like history of programming languages, as you know. But yeah, really cool talk, thanks.
I would, if you don't mind, just like to comment on Connor's question about what languages influenced what. I set about to do a C++ weekly episode on the languages that influence C++. And I noticed that every edition of the C++ programming language by Bjarne gives a different list of languages that influenced C++. So I just feel like I don't know anything anymore.
Really?
Yes.
Yeah. Do you have like the different versions?
I was able to pull up a couple of different versions. Well, he has the introduction to each edition is maintained in the book. So you've got that information. And I think I was able to pull up one of them on my Safari membership or something at the time.
Interesting. I would love to see, well, that C++ weekly episode I'd love to see in general, but if it includes a delta of like the evolution of what Bjarne says influenced it.
Well, I think Ben has ultimately at some point promised to do that C++ weekly episode as a guest spot.
Ooh.
Can you hear me? First,
yes.
Can you hear me? My mic broke in my headset. I'm pretty sure. Just had to order another headset. I've had trouble all night. But now I'm on the fancy mic, so hopefully it works. Yes, I still kind of have that in mind. Have you, Jason, have you read Design and Evolution? Because there's a bunch
I haven't. I'm guessing it has another list.
Languages.
Yes.
Yeah.
And Wikipedia doesn't agree with any of the others, just for the record.
Huh. I was going to say, Connor might find this interesting. So well, everyone might. The syntax for defining types in ML uses. So I don't know if this is absolutely true. I think it's true. It uses the star.
Yeah.
Right. For basically because they're product types that get defined. So what we would think of as structs or tuples in type theory are product types, and ML uses the star to define them for that reason.
Interesting. I had a big discussion with a professor in Toronto just on, was it Tuesday, right after our Monday meetup? And he was mentioning, we started talking about continuations, which I know nothing or knew nothing about at the time. And that like SML NJ, which is something I had never heard of, the standard ML of New Jersey came up. And anyways, in his explanation of the history, he said that basically, like ML came straight from Lisp. I think it might have been Scheme, and that like basically ML started off as like a statically typed scheme. I might be getting that wrong though. It was a Lisp dialect that like plus static typing that led to ML. And then I realized there's like this whole history ML languages that I need to now go add to my list of things to learn. It's ever growing.
ML
yes.
was the first. ML was the first language they taught in my university course. We totally didn't appreciate it at the time.
That's because he went to Hogwarts, just for the record.
And yeah, let's all we got to start pinging Ben. Let's go, Ben, for that C++ weekly. Let's go, Ben.
I did suggest it to Jason, what, about a year ago now?
It's been a while. It might have been more than that at this point.
Maybe we should just everyone who has a meetup should just, that Ben attends, should just, and we're looking forward to the upcoming C++ weekly. At some point, everyone's going to start talking, I heard about this episode that's coming out soon.
So if I may, for the sake of this recording here, if there's any other questions about Leslie's talk, then let's do those, and then I'll stop the recording, and then we can just transition into happy hour chat time.
So you are really quiet.
Yeah, Tim, your volume's really low somehow.
Can you hear me now?
Still quiet.
Speak loudly.
Does this help if I'm loud?
That's good.
You can hear me?
Yes.
Okay. Yeah, so just two questions. I guess the first question, in the C++ examples, it seems like a lot of them could be pure functions. I'm wondering, is there a reason you didn't use overloading as much? I mean, you're complaining about inheritance, but is that just because you wanted to use inheritance?
No, because I need to put them into a tree.
Oh, for the tree example, but what about, like, it seemed like you use it quite a bit, some of the other examples.
Basically, I need to put this shape into the tree. So it's hard to not use inheritance. For the material, I can probably get away without inheritance, but that means also I need some kind of dynamic polymorphism for material. Because different shapes have different materials, and shape is already like, dynamic.
Okay, and I guess another comment, I was just curious, so you're like newing the tree, like the different nodes in the tree. I was wondering, like for performance, to reduce the amount of news, like would you consider putting it in like a vector?
This is an excellent question, because in one of the book called Physically Based Rendering, they did exactly that. And yeah, it will be helpful, but I haven't played with that yet.
Okay, cool.
So I just want to go ahead and thank Leslie. We'll wrap up the recording here, but of course, everyone's free to hang out as long as they want to. I'll also hand off control of the meetup to Leslie. Thank you. I feel like this was an awesome follow-on to all of the things that we've been talking about the last few months at our meetup here. And yeah, that was great. Thank you. So
Thank you. Yeah, thank you very
virtual
much.
hand claps.
Thanks.
All right.